Hi, this is Alex from devstories.eu. SunPy, Solar Data Analysis, Episode 12 of 12. The Sun is not a solid rock. Its equator spins significantly faster than its poles, meaning any coordinate grid you map onto it is slowly tearing itself apart. If you track an active region on Tuesday, those same latitude and longitude values will point to empty space by Thursday. To track the actual plasma, you need a mechanism called modeling differential rotation. People often treat celestial bodies like solid spheres. On Earth, a geographic coordinate stays put. On the Sun, the surface is fluid. Plasma at the solar equator completes a full rotation in about 25 days, while plasma near the poles takes over 34 days. Because coordinates are inherently time-dependent, you can't just carry over a spatial position from one day to the next. You have to account for the physical shift of the solar material over time. SunPy handles this time-dependent shift using a coordinate frame called RotatedSunFrame. This frame lets you take a coordinate measured at an initial time and project where that exact parcel of solar material will be at a new time. Here is the key insight. RotatedSunFrame acts as a wrapper around an existing coordinate frame. You do not calculate the new latitude and longitude manually. Instead, you define a frame that explicitly encodes the time difference, and you let the coordinate transformation engine do the math. Suppose you have the coordinates for an active region observed on Tuesday. This is your initial point, represented as a sky-chord object. It has a spatial position and an observation time. To find where that active region will be on Thursday, you set up a new rotated sun frame. First, you provide the base frame, which you extract directly from your Tuesday coordinate. Next, you provide the target time. You can specify Thursday's exact time step, or you can pass a duration, like a 2-day time delta. SunPy now has a target coordinate frame that understands the solar rotation model. Finally, you take your Tuesday coordinate and transform it into this new rotated sun frame. When you run this transformation, SunPy applies a standard differential rotation profile. It reads the latitude of your starting coordinate, calculates the correct angular velocity for that specific latitude, multiplies it by your 2-day duration, and shifts the longitude. The output is a new coordinate object. Its latitude and longitude are updated to reflect 2 days of differential rotation, pinpointing exactly where your active region plasma has drifted by Thursday. If the region was near the equator, it shifted a large amount. If it was near the pole, it moved much less. This approach allows you to step coordinates forward or backward in time seamlessly. Because differential rotation changes the physical location of the data you're studying, tying every coordinate to a specific observation time and shifting it through the rotation model is the only way to maintain accuracy across multiple observations. That wraps up our series on solar data analysis. I encourage you to explore the official SunPy documentation, try these tools hands-on, or visit devstories.eu to suggest topics for future series. That's all for this one. Thanks for listening, and keep building.